The dynamics of winds in Earth's atmosphere go beyond the simplistic explanation that pressure differentials alone cause them. If pressure alone dictated winds, we would observe steady, predictable airflow rather than gusty and turbulent winds that we actually do experience. Focused, powerful winds emerge due to a more complex phenomenon: vortices. Vortices act as the atmosphere's pressure relief valves. Without vortices, pressure differentials would be significantly more intense since gases alone cannot sustain structured streams. For a stream of wind to form, a sheath that isolates the flow from the natural friction and dispersive qualities of gases is required. Vortices, often invisible but crucial, form this sheath through a plasma of water nanodroplets that spin up along wind shear boundaries in the atmosphere. When you see a tornado, you're not merely witnessing a mix of gases like nitrogen, oxygen, and water vapor. Rather, you're observing a phenomenon in which the surface tension of water nanodroplets maximizes due to wind shear, creating a structured plasma. This plasma forms the sheath of the vortex, enabling winds within to accelerate up to 300 miles per hour with minimal friction. The field of meteorology, despite its prevalence, is filled with speculative notions often aimed at simplifying complex atmospheric phenomena for public consumption. Meteorologists rely on anecdotal interpretations rather than empirical science, crafting explanations that appeal to the broadest audience, often at the expense of scientific accuracy. They overlook vortices, which are far more intricate than commonly assumed. Most people only notice vortices during their final stages, such as in the low-pressure conditions associated with storms. At this point, the residual momentum of larger vortices drives the gusty winds we associate with storms. This gives the false impression that vortices are a byproduct of storms when, in fact, they are the cause of both the storm and the low-pressure winds. Some conventional meteorological theories, like the notion that warm air rises and causes low pressure, are fundamentally flawed. For example, meteorologists commonly argue that warm, moist air is lighter than dry air, and that its rising causes the low-pressure zones that drive storms. However, this is contradicted by the fact that warmer air, being wetter, is actually heavier than dry air. The assumption that warmer air always rises is only valid in arid conditions, like in deserts. In most other environments, vortices high in the troposphere are responsible for the uplift that creates the low-pressure conditions we observe, not convection. Despite the consensus on convection within meteorological circles, it is a misguided model. The uplift in thunderstorms, for instance, results from the low-pressure energy funneled by vortices from jet streams, not convection. The common belief that convection generates low-pressure systems is based on an analogy of a pot boiling on a stove, which is a far cry from the empirical reality of atmospheric dynamics. Vortices are integral to understanding atmospheric flow, storms, and wind patterns, yet they are ignored in favor of oversimplified models. The explanation of warm air rising over cold air to form storms, as proposed by many meteorologists, ignores the role of vortices in the actual physics of atmospheric dynamics. As vortices channel energy from jet streams and form boundaries between moist and dry air, they drive both uplift and cooling, which leads to condensation and precipitation. In short, real atmospheric science must shift its focus to vortices. These structures, often invisible but undeniably powerful, are the true drivers of many atmospheric phenomena, from jet streams to tornadoes. Simplistic notions like convection fall far short of explaining the true nature of storms and winds. Scientific inquiry must move beyond these anecdotal models if we are to truly understand the complexity of Earth's atmosphere.